In the last two videos, we talked about systems of ODEs, and a result was a whole collection of functions. In fact, for an n-by-n system, we always had n arbitrary constants. You could even say that our solutions actually form an n-dimensional vector space of differentiable vector-valued functions, if you want to be very precise about it. So, but most of the time, when we solve an actual real-world problem, we expect to get a single answer. We don't expect to get this entire vector space of answers. That's not going to be very useful most of the time. So what do we do? Well, in a real world problem, we're also going to have a little bit more information about our function. We're not just going to have our differential equation or system of differential equations y prime equals ay. We're also going to have what we call an initial value. We're, it, so we've been using t as our variable, and usually people use that because we want to say t is time. We're talking about a function or a collection of functions that changes over time. But we know something about what our function is doing at some starting time, an initial time. Or in other words, what happens if we put in 0? We'll have some value y of 0. Now, what we're actually looking at here is different values for all of our y's. So y1 at 0 is some b1, y2 at 0 is some b2, until we get to some yn of 0 is some bn. So we know where our functions start, and our differential equation is going to tell us how those functions change over the course of time. If we have a differential equation and this initial condition, we're going to call this initial value problem. It's not the only way that we can have conditions on our differential equation that actually work out, but it's definitely one of the simpler ones. Other ones that you might actually encounter or might hear about are what are called boundary value problems. Those can actually be much more complicated and not necessarily have solutions that do fit those boundary conditions. Initial value problems are very nice because if you have an initial value problem with some conditions on things being differentiable and all that kind of stuff, but most initial value problems will have a unique solution, and that's the main thing that we want. So what do we do with this? Well, we're going to start off by solving our differential equation, our system of differential equations, how we were doing it before. So we start with this, we solve it, and we get what we call our general solution. And then we apply the initial condition. So we apply the initial condition and solve to get our actual solution to the initial value problem. So let's actually just put this into practice. So we have problem 2. So problem 1 was all just finding general solutions. Problem 2 is going to be initial value problems. They're the same kind of problems that we had in part 1, but we have this extra condition on what are our functions at t equals 0. On your homework, you're going to work on parts A and B. I'm going to do parts C and D here. I did give you the 2x2 systems. We're actually going to have 3x3 systems in this one. So this will be a lot of fun. So we have 3 functions. We're going to turn this, we're going to ignore the initial condition for the moment. We'll come back to that later. But we're going to turn the system into a matrix. But it's a 3x3 matrix here. So we have to take into account what this actually is. So y1 prime is written in terms of y1 and y3, but we can't ignore the fact that there's a 0 times y2 in here. So really our first row is 2, 0, negative 6. Our second row is 1, 0, negative 3. And our third row is 0, 1, negative 2. We're going to then go ahead and subtract lambda from each of our diagonal elements. Remember that this 0 here is going to be a negative lambda. And we get to actually take our determinant here. So this will be lots of fun. We have 2 minus lambda times the determinant of this part. That part is negative lambda times negative 2 lambda, or sorry, negative 2 minus lambda. I'm just going to write that out. I might not go through all the steps of actually expanding everything after this point, but I'm actually going to go ahead and write out the terms that we have here. So we're subtracting negative 3 times 1, so we add 3 to that. The 0 here we're taking advantage of to not have to deal with that term. Then we also have the negative 6 times, now we have 1, well, minus 0. That 0 is very nice there. So this is actually a lot simpler than it could have possibly been. If we expand everything out, we can actually see that we get negative lambda cubed, because we're dealing with the 3 by 3, we expect to get a negative 1 as our first coefficient. Then we get a plus lambda, which actually means if we pull out negative lambda, we get lambda squared minus 1. And lambda squared minus 1 is actually just lambda minus 1 times lambda plus 1. And we want that to equal 0. So our lambdas here are 0, 1, and negative 1. Those are our eigenvalues. And we have to deal with all of them. We can't ignore any of them. So lambda, let's say this is lambda 1. Lambda 1 equals 0. So we're going to take our matrix A. I'm going to try to fit them all on this page. We'll use another page for the actually solving the equation. We're going to then go ahead and use row operations to simplify this thing. Of course, you can probably easily see here that we can just move our second and third row to the first and second, and then actually use those to cancel out. Actually, we only need the second row to cancel out that first row. So we're left with negative 3, minus 2, and 0. Which means if we then, I guess calling this x1, our first eigenvector, if we plug in 1 for our third component, our second component is going to be 2, and our first component is going to be 3. Then we'll use our second eigenvalue. I'm going to say the second one is 1. The order of these doesn't really matter, but it's nice to keep the lambdas and the x's straight, so we know which one goes to what. Now we're going to subtract 1 from each of our diagonal elements. That means we have a 1 here, we have a negative 1 here, and we have a negative 3 here. Everything else is the same. And then we do the same kind of thing. Actually, let's go ahead and leave our 1, 0, negative 6 as our first row. I'm going to put the 0, 1, negative 3 as our second row. And then it shouldn't be too hard to see that the second row that we started with is just a combination of the first and third rows. In fact, it's the first row minus the third row. So we can cancel that one out. Of course, we always expect that when we're doing an eigenvector problem, because we know this is a singular matrix. Because, well, if we plugged 1 into here, we get a determinant of 0. Alright, so going ahead and putting 1 for our third component again. The second component is going to be 3, and the first component is going to be 6. Alright. Now, wait, sorry, that's going to be, lambda 3 is negative 1, sorry. Now we're subtracting negative 1 from our diagonal elements, which means we're adding 1 to them. So we have a 3, 1, and negative 1. Everything else is still the same. We go ahead and use our row operations again. This time we're going to do a little bit more. I'm going to use this second row as my first row, but I'm also going to use this third row to cancel out the 1. I'm going to be left with a 1, 0, negative 2. I'm going to make my third row here into my second row. And then, of course, as we expect, the original first row is going to be completely canceled out. We're going to leave the actual showing of that, the actual working of that out to you. But again, I'm going to pick 1 for my third component, just because that's the easiest thing to do. That leaves 1 for our second component and 2 for our first component. So these are our 3 eigenvalues with our 3 eigenvectors. Now we go ahead and actually combine all that stuff. So we have our y is equal to c1 e to the, well, 0t. Our first eigenvalue is 0. So actually, let's just go ahead and leave that out, because e to the 0t is 1. So we have c1 times our first eigenvector of 3, 2, 1, plus c2 e to the lambda 2 is 1, so just e to the t, times our x1, or sorry, not x1, x2, our second eigenvector, is 6, 3, 1. Then c3 times e to the lambda 3 is negative 1, so we have a negative t. And our x3 is 2, 1, 1. Or in other words, if we actually write this out, we have 3c1 plus 6c2 e to the t plus 2c3 e to the negative t. Then we have 2c1 plus 3c2 e to the t plus c3 e to the negative t. And then finally, all the third components of our eigenvalues, our eigenvectors, are 1. So you have c1 plus c2 e to the t plus c3 e to the negative t. Now, what are we going to do with this? Well, remember, we need to apply our initial condition. Our initial condition is that when we plug in 0 for t, all these functions equal 2. So let's go ahead and plug in 0. Plug in 0 for our t's. Well, one of the advantages of doing this, especially for when we don't have complex eigenvalues, is that anytime we have an e to the something times t, that becomes 1. That's why we like to have 0 here, because it's much easier. If we have a different initial condition, things get a little bit more complicated. We end up with extra e's in our formula. But I'm not going to give you any problems that where we don't plug in 0. So what does this turn into? We get 3c1 plus 6c2 plus 2c3. Then we have 2c1 plus 3c2 plus c3. And then finally we have c1 plus c2 plus c3. And the point is that each one of these are just y1 of 0, y2 of 0, and y3 of 0. All of those are going to equal 2, because that's what our initial condition said. So this is what we're trying to solve. We're trying to find out c1, c2, and c3 where this is true. But notice that we actually just have a system of equations. We have one equation equals 2, another equation equals 2, and a third equation equals 2. And these are always linear equations. So really, we're just trying to solve a linear system. It comes back to stuff we already know how to do. I'm going to put this as an augmented matrix. So we have 3, 6, 2. 2, 3, 1, and 1, 1, 1 with an augmented part of 2, 2, 2. And we're just going to solve that. What are our c's in this case? Well, obviously I'm going to move the 1 here to the first row. I'm going to use that to cancel out the other rows. That'll actually leave me with a 1, negative 1, negative 2, a 3, negative 1, negative 4. And I'm not going to go through all the actual process of this. You guys should know how to do that by now. I'm going to use this 1 to cancel out the 3 and this 1. It'll be nice to actually just not have anything else in that column. So those will go away. We'll be left with a 2 and a 4. This is still going to be the same as the negative 1, negative 2. And this one becomes a 2 and a 2. And then our last step is we're going to go ahead and use this 2 here. We can actually divide this last row by 2, and then use that to cancel out these other ones. So I eventually get down to identity matrix. That should be a 0. And over here I have 2, negative 1, and 1. Those are my c's. C1 is going to be 2. C1 is going to be 2. C2 is going to be negative 1, and C3 is going to be 1. So I can actually just go ahead and put those in. That are y, in this case, putting those in here, is going to be 6 minus 6e to the t plus 2e to the negative t. Then we have 4 minus 3e to the t plus e to the minus t. And then finally, just 2 minus e to the t plus e to the minus t. And these are y1, y2, and y3 that both solve this system of equations, or this system of ODEs, but also satisfies that condition. And that's what we're looking for. So, kind of a long process. I mean, we had that initial process of having to solve the differential equation, but then the extra process of having to actually solve for our coefficients. But that is what you have to do. That's the whole idea behind being able to do all this stuff. Let's do it again. Let's give you another example of it. So again, so working on problem 2, same actual instructions here, but just a different problem. So again, this is a 3 by 3 system. We have 3 functions. So we're going to have a 3 by 3 matrix. So 1, 0, 2, then 0, 1, negative 1, and 1, 1, 1. So kind of nice, smaller numbers this time at least. But that may not mean that everything comes out nicer. Maybe it won't. We'll have to see. Go ahead and subtract lambda from each of our diagonal elements. Everything else is the same. Sorry, that should be a 0. We go ahead and expand this thing out. We have this lambda, 1 minus lambda times this. So we have 1 minus lambda times itself, so we actually have it squared. Then minus a negative lambda times 1, or not, sorry, negative 1 times 1, so we add 1. The 0 here we're using to not have to do that part. Then we have a plus 2 times this part. So we have 0 minus 1 minus lambda times 1. So lots of fun with that one. If we expand everything out, we get a negative lambda cubed plus 3 lambda squared minus 2 lambda. Now, of course, what they've actually done here is that they made a situation where our constant is 0. In other words, the determinant of the original matrix is 0. So we can pull out a lambda. In fact, I'm going to go ahead and pull out a negative lambda. And I'm left with lambda squared minus 3 lambda plus 2, which I'm also going to go ahead and factor as lambda minus 1 and lambda minus 2. So, have to be able to factor here. All the fun stuff is coming into play, isn't it? But the important thing is that we have actual eigenvalues of 0, 1, and 2. So, say lambda 1 is 0. That means we're taking our original matrix, and we're going to use raw operations to simplify it. It means I'm going to leave these first two rows alone, but then the third row is going to become all zeros. It was singular to begin with. One of our rows we could have canceled out. That gives an x1 of negative 2, 1, 1. Again, I'm picking 1 for our last one, and that means we get 1 for our second one and negative 2 for our first one. Then we have our eigenvalue of 1. We're going to subtract 1 from each of those, which is actually kind of nice because they all become 0. Everything else is the same. I'm going to move my third row to my first row, and then I'm going to take my second row and divide it by negative 1, and use it to cancel out that 2. So here, actually my third variable this time is not free. The third variable has to be 0, because remember this basically means, you could say that z equals 0 is the second equation. So we have 0 there, and now our second variable is our free one. So I'm going to make that one, make it 1, which means we need negative 1 for our first variable. Finally, this should have been 2, sorry. Our lambda 3 is 2, which means we subtract 2 from each of our diagonal elements. Now we get negative 1s instead of zeros. Go ahead and do all of our row operations again. Actually, our first two rows here, we can just multiply by negative 1 to make it easy on our. So we have 1, 0, negative 2, and 0, 1, 1. Of course, our third row is actually going to cancel out. You should go through the steps of doing that, but I've already done that. But the important thing here is that we can, again, set our third variable to 1, means we get a negative 1 for our second one, and 2 for our first one. So those are our eigenvalues and our eigenvectors. And we're going to use those to actually solve this differential equation, this initial value problem. So now we go ahead and put our solutions together. We have our y is equal to c1 e to, well, our first lambda is 0. Lambda 1 is 0. So e to the 0t is 1. Our x1 is negative 2, 1, 1. Then we have c2. We have e to the 1 times t, so e to the t. Our x2 was negative 1, 1, 1, or sorry, negative 1, 1, 0. Then we have c3. This time our lambda 3 was 2, e to the 2t. And our x3 was 2, negative 1, 1. So again, if we put this all together, what do we get? We get negative 2 c1 minus c2 e to t plus 2 c3 e to the 2t. Then we have c1 plus c2 e to the t minus c3 e to the 2t. And finally, c1 plus, well, that's a 0, so that's nice. So we get plus c3 e to the 2, that's a 2, 2t. What do we do now? Well, we go ahead and we use our initial condition. We're going to look at y of 0. We plug 0 in here, all the e to the t's become 1s. all the e to the 2t's become 1s. So we're left with negative 2c1 minus c2 plus 2c3. We have c1 plus c2 minus c3, and a c1 plus c3. But remember, that's supposed to equal, here, y1 and y2 are both 1, and y3 is 4. So this is supposed to equal 1, 1, 4. Again, this is a system of equations. We can solve it the way we know how to do that. So we're going to set this up as an augmented matrix. We have negative 2, negative 1, 2, 1, 1, negative 1. And of course, we do need the 0 here with our augmented part of 1, 1, 4. Go ahead and I'm going to move my third row to my first row. Then I'm going to use that to cancel out the other two things in that column. I'll be left with a 1, negative 2, negative 3, and negative 1, 4, 9. I'm going to use that 1, so I'm going to keep that row. Then I'm going to use it to cancel out the negative 1 that we have there. I already had a 0 here, so that was nice. But my last row is going to be now a 2 and a 6. Of course, I can go the next step and divide that by 2. Sorry, getting a little ahead of myself. And then I'm going to use that 1 or even that 2 to cancel out the other things in that column. So we have 0, 0, and we're going to be left with a 1 and a 3. So C1 is going to equal 1, C2 and C3 are both going to be 3. And so what do I have? My solution here, my y, so let me put that a little bit lower, y is going to equal negative 2 minus 3 e to the t plus 6 e to the 2t, then 1 plus 3 e to the t minus 3 e to the 2t, and then finally 1 plus 3 e to the 2t. Those are my y1, y2, and y3 that satisfy my differential equation, my system of differential equations, and also satisfy my initial condition. So, again, very similar process. Of course, it would be a little bit more complicated if we had to deal with complex eigenvalues, but we'd do the same kind of thing. We'd still plug in 0. There, we'd have to remember that cosine of 0 is 1 and sine of 0 is 0. But hopefully you guys remember that stuff. But it would be the same process. You'll get a linear system. You solve that linear system to get your constants, and then you put the constants into your formula. You do the exact same kind of thing. So it's not that putting an initial condition actually makes it more complicated, at least conceptually, but it does make more work. It's almost kind of busy work, but it's important that we know how to deal with that. Alright, we have one more video, kind of a long section here, but we're going to actually stop looking at just our first order equations and actually look at higher order ones. So pay attention to the next one. It'll be important to at least one of your homework problems.